the biggest number. So maybe, for example, 98% you have a chance to get the ground state from the system. And you see that that's the reason that it's not very useful for me, for example, if you think about the probability like efficiency, you know, efficiency. You want to get more outcome from the system, efficiency. So the efficiency to use to make a system with the lower energy level should be very high if the system had the negative energy, because hydrogen atom has the negative energy. And if you find I mean, if you have a number of the systems, I'm not in the detail of the system, but I know that they have a different energy levels. And my interest is that to get the most probably state, I want to know that which configuration of energy have the maximum probability. For example, it will be some number near 1, yes, maximum probability, 98%. What you don't expect is that the maximum probability comes from the lowest energy level, if the system all are in the equilibrium. Of course, not in equilibrium, like some systems are not in equilibrium, for example. They have a transfer of the particles between each other. They have a transfer of the energy to each other. That will be the next lecture about the grand canonical systems. In canonical system, what you are thinking is that you never think about the about the sending the particle from the one part of the system to the other part. So, and you consider the system, the whole energy system of the system fixed. So the maximum probability comes from the lowest energy level of the system. So it seems that in the large number of the particle which have the part of the system which have the lowest energy is more efficient for you, is more effective for you, and you don't expect that, huh? I mean, if you translate that to the social life, but this example is not correct, but just I want to tell you that you have some giant people here in the society, yes, very giant people, and you have some very big people here. And the number of the system is very big, so of course Avogadro number is very big, so about 1 million people, for example. And the big people has the lowest income, I mean lowest money and everything. So the most efficiency will come from the lowest, from the poor part of the community. It's not very, like, because they are millions, so in some sense you can say that their number is big. So the giant people, the highest energy level doesn't have more probability or chance to catch. And that's true, yes? Normally, lowest percent of the people in the social community have the highest number of the income or something. So I mean the chance of finding the system with the highest energy level is lower.
Yeah. We get it.
So, but be careful that, because the statistical physics and all theoretical physics is about particles. So I don't think that it's easy to use this concept for the social life, even for the human cells, for example. I don't believe to that personally. That, for example, you can use these interpretations of the wave function, because they use, there is a subject tomography, for example. This subject tried to use the concept of quantum mechanics to simulate the form of the cancer, for example, tumor. So maybe this is just formal, so I don't think that you can use do you know what's the difference is that, because this is what I need to say, that the human system, human means the we, animal and everything. So they are not predictable. No?
Yeah.
They change their decision in a few minutes, few seconds. But the physical systems are predictable. If you put a million hydrogen atoms together and if you fix it for them the total energy, I can definitely tell you that what is the probability of that, what is the pressure, what is the they are very organized. So, but the human cells, for example, they are not organized. There are very similarity between, if you, this is a just formal, I mean, take this, consider this example just very formal. So, I think better for you, because really it's very confusing to use the concept of the physics for the other subjects. This is my personal. So think about this question and try to find a good functions, good function for hydrogen atom to estimate the energy. You know what is the energy level of the hydrogen atom is? Yes.
-13.6.
Yes, it is -1/4 pi epsilon E over A0. Right. Let me to write here the Coulomb constant because I want to have this. Yeah. Because this is a Coulomb iteration, 1/4. So I want to. This is this A0 is
Distance between two.
Angstrom is the Bohr values. Try to get some number near close to that by trivial function. I know I can find that exactly from the wave function of the hydrogen atom. I will give you the exact wave function, okay? The exact wave function for the ground state of hydrogen atom is that. We call it psi 110, or we call it that R theta phi. This is just different symbol. It's 1/radical pi r cubic e minus r over a0. This is the exact wave function. But I don't want you to use that. So find a trivial function, like what I did here. And the boundary condition is that, just we have one boundary condition, unfortunately. The limit any function you choose when r tends to infinity. And it should be regular at r0. Limit this function r tends to the 0 should be less than infinity. For example, 1/r, no, you cannot choose 1/r. This is what you expect is maybe good, huh? As a phi. Because 1/r satisfies that, but it's break that. So try to find another. This is the exact. We are lucky because we are able to solve the Schrodinger equation for hydrogen atom, but not always. And you can't imagine that how this is important. So we need to finish the lecture. So we will continue next lecture. So